Stage 5 of model-based inquiry is called establishing credibility. This is the culminating stage of an MBI unit, where students bring together everything they have learned to construct final, evidence-based explanations of the anchoring phenomenon. Up to this point, student sense-making has been supported through group models, public records, and whole class consensus building. In Stage 5, students take responsibility for explaining the phenomenon individually, while continuing to refine their thinking through interaction with peers. In model-based inquiry, writing an explanation is not simply a way to show what students know. It's a sense-making practice, another opportunity to build knowledge. Students begin this stage by drafting individual evidence-based explanations using the criteria established at the end of Stage 4. These criteria are captured in the Gotta Have checklist, which outlines the important science ideas that must be present and the evidence that supports them. Like modeling earlier in the unit, explanation writing is a practice that leads to a product. As students decide what to include, how to sequence ideas, and how to connect claims to evidence, they are actively refining their understanding of the phenomenon. In MBI, explanations do more than describe what happened. They explain how and why the phenomenon occurred by coordinating claims with evidence and science ideas. Strong explanations make clear claims about the phenomenon, support those claims with evidence gathered through investigations, and use science ideas to show why that evidence matters. Explanations are expected to be coherent, complete, and persuasive, not just correct. The Gotta Have checklist supports this work by helping students ensure their explanations are gapless, meaning that all the important ideas identified by the class are addressed and supported by evidence. In the Hindenburg unit, students write explanations that account for the rapid ignition and destruction of the airship. As students draft, we can see full written explanations on the screen. These explanations coordinate multiple ideas: the use of hydrogen as a lifting gas, the mixing of hydrogen and oxygen, the need for activation energy, and evidence from the Exploring Energy Lab showing how chemical reactions can release large amounts of energy quickly. Strong Hindenburg explanations do more than name hydrogen as flammable. They explain how hydrogen and oxygen molecules interacted, what provided the activation energy, and why the reaction was exothermic, using evidence and representations developed across the unit. In the Lamcillus mussel unit, students write explanations describing how lifelike mantle lures evolved over generation. On screen, we see students' explanations tracing the mussel life cycle, the challenge of delivering larvae to host fish, and how variation in lure traits affected reproductive success. These explanations coordinate ideas about mutation, genetic recombination, natural selection, and selection pressure from host fish, supported by evidence from tasks like I Will Survive and other investigations. In both units, students use the Gotta Have checklist to guide their writing, ensuring that their explanations are coherent, complete, and grounded in evidence the class has agreed upon. After drafting these explanations, students engage in peer review. This process is intentionally structured using the MBI Explanation Peer Review Guide, which focuses students' attention on the most important features of explanations without reducing the task to a checklist. Through peer review, students read one another's explanations, ask questions, and offer feedback about clarity, completeness, and use of evidence. This creates additional opportunities for argumentation and negotiation as students encounter differences in reasoning or notice ideas they may not have considered. Teachers support this process by making explicit that explanations, like models, are refined over time through interaction within a community. Students then use peer feedback to revise and finalize their explanations. In doing so, each student's explanation gains credibility, not because it was approved by the teacher, but because it has been tested and refined through engagement with peers who have also invested deeply in understanding the phenomenon. This mirrors how explanations gain credibility in the scientific community, where ideas are refined through discussion, critique, and review. Assessing students' final evidence-based explanations is an important part of establishing credibility. In model-based inquiry, assessment is aligned with the same criteria students have used throughout the unit to make sense of the phenomenon. Rather than focusing on surface features or correctness alone, the MBI explanation rubric attends to how well students coordinate claims, evidence, and science ideas. It emphasizes coherence, completeness, and the quality of connections students made between evidence from investigations and the ideas needed to explain the phenomenon. Because students have worked with the Gotta Have checklist, engaged in peer review, and revised their explanations, Assessment becomes a continuation of sense-making rather than a separate or hidden judgment. Teachers can use the MBI rubric to evaluate students' explanations while also gaining insight into where students are in their reasoning and how they might be supported moving forward. Establishing credibility completes the model-based inquiry cycle. It ensures that students leave the unit not just with answers, but with explanations that have been developed, challenged, and refined through scientific practice. To learn more about model-based inquiry and support students in constructing explanations, visit modelbasedinquiry.com.